Hey, how's it going, guys? I'm going to go through question 1 from the Chapter 6 free response questions and also include the point totals for each, just so you guys can see me work through it and know where all the points are coming from. So let's dive right in. A block of mass M is pulled along a rough horizontal surface by a constant applied force of magnitude F1 that acts at an angle theta to the horizontal. The acceleration of the block is A1. Express all algebraic answers in terms of M, F, theta, and A, and fundamental constants. All right, so part A, I'll tell you right off the bat, 4 points out of 15 come from part A. All 4 of those points are going to be from this free body diagram right here. All right, this should be the easiest 4 points that you get on this problem. We've got the force of gravity down, and we've got the normal force back up. You've got F1 pulling at some angle, and then you've got force of friction going back. There are your 4 points right there. It did not want you to break it up into components. That's it. All right. Notice that my normal force is not as long as my force of gravity. That's because you've got a component of this F1 that's also going to be helping along with it. All right. But that's where you're getting your 4 points from. Let's move on to part B. Derive an expression for the normal force exerted by the surface on the block. All right. This is where we're going to start splitting things into components, okay? Now, one thing that it says in the scoring guide is that if you're going to split it into components, draw a different diagram. It doesn't want you doing it on this diagram, okay? So let's look at the forces that are simply acting in the Y world. We've got force gravity down, we've got normal force up, and then we've got the component of force 1 in the Y direction. All right, now that component of force 1 in the Y direction, if I draw this out, here's force 1. This is the X component. That's the Y component. Here's theta. The Y component is going to be F sine theta, and the X component is going to be F1 cosine theta. All right, so let's go ahead and figure out the normal force. The normal force is in the Y world. I have no acceleration in the Y world. Therefore, I can say that the sum of my forces in the Y world is equal to 0. This means that and then if I rewrite this equation for the things that are acting in the Y world, I'm going to get F1 sine theta plus my normal force minus mg. Now, it wants me to get an expression for normal force, so I'm just going to rearrange this so that I get normal force is equal to F1 sine theta. Actually, I don't want to do that there. Normal force is going to be equal to mg minus F1 sine theta. All right. Now, on this one, you get 1 point for this step right here at the beginning, which is simply writing that equation out, and then you get 1 point for the correct answer. So part B had 2 points. So we're already at 6 points total out of 15 on this problem. Moving on to part C, I'm going to kind of move all this here real quick. Give me 1 sec. Group that. Okay, move this up here. Let's look at part C. So part C, derive an expression for the coefficient of kinetic friction mu between the block and the surface. All right, now we're going to be looking at what's going on in the X world, okay? So according to the beginning of this, we do have an acceleration, all right? The acceleration of the block is A1, all right? Now, that's going to be important to consider because what this means is that our net force in the X is not 0. All right, so because our net force in the X is not 0, our net force in the X is going to be equal to mass times acceleration in the X. Acceleration in the X is equal to A1. All right, so let's look at the forces that are acting in the X world. We've got force of friction, and we've got F1 cosine of theta. almost wrote sine there. F1 cosine of theta. And that's it. All right. So we put those into our equation. We've got m times a1 is equal to F1 cosine theta minus the force of friction. Now, I need to substitute force of friction in for the equation that represents force of friction. That's going to be m times a1 is equal to F1 cosine theta minus mu times the normal force. All right? That right there represents 1 point on this problem. So if you can get to that point, you've earned yourself another point. The next thing that we need to do, though, is we need to get an expression for mu. We need to get this expression for mu in terms of the things that are specified at the beginning, which are just simply m, F1, theta, and A1. So normal force is not included in that. Fortunately, though, I have an expression for normal force that I got over here at the beginning. So we're going to sub that in. So we're going to get m times A1, and I'm actually going to bring F1 cosine theta to the other side. Actually, I'm going to do this the opposite way. I'm going to get mu times the normal force, which was mg minus F1 sine theta is equal to F1 cosine theta minus m times A1. So that simply was a substitution right there, and I put mu and normal force on a side by itself. Again, let's see if I can do this a little bit faster this time around. Maybe not. There we go. All right. Now all I need to do is simplify that expression to get mu by itself. So I'm going to divide by mg minus F1 sine theta, and I get that mu is equal to F1 cosine of theta minus m times A1 divided by mg minus F1 sine of theta. Boom. There is your second point on part C. Second point. So the big thing there was recognizing, one, that you have a net force that is not equal to 0, and then setting that equal to mass times acceleration, because net force is equal to mass times acceleration, Newton's second law. And then once you get to this point here, realizing that you need to substitute in your expression for normal force that you solved for in part B. All right? Moving on to part D. So, part D, we have an object that is accelerating at a constant rate. So, what that means for us is that our velocity is going to be getting higher at a constant rate. Our velocity is increasing at a constant rate. We've got something that looks like that. What this means for our position is that our position is, the velocity is changing, therefore our position is also changing. Its slope is going to be an increasing slope in the positive direction. You get 1 point here, you get 1 point here, and then you get an additional point for the graphs being consistent with each other. All right? Now what that means is, let's say that I had put that my object is slowing down, and that would be something like this. I wouldn't earn the points here, but I would earn this point because my graphs are at least consistent with each other. Okay? So above all else, just make sure that you're being consistent in your work, because you never know, you might earn some free points at some point. All right? Moving on to the final part. I think this is the hardest part about this problem. So, if the applied force is large enough, the block will lose contact with the surface. Derive an expression for the magnitude of the greatest acceleration that the block can have and still maintain contact with the ground. All right. The biggest thing here is this statement right there. There's a certain point where the applied force is so large that the block is going to lose contact with the surface. It is at this point that your normal force is equal to 0 newtons, because guess what? There's nothing touching the ground anymore. All right? If your normal force is equal to 0 newtons, what this means is that at that point, your frictional force is also equal to 0 newtons. The reason for this is because your frictional force is equal to mu times the normal force. Well, if there's no normal force, then you can't have a frictional force. All right? So, let's go ahead and look at what we do here then. Again, we're going to sum together our forces in the x world. We still have an acceleration in the x world, so this is mass times the maximum acceleration. That's what we're looking for here. Now, at this moment, all right, or we can think of right before this moment happens, this is where our block loses contact with the surface. Therefore, the only force that's going to be acting in the x direction is this force, this component of F1. So that component of F1 was F1, or we'll call it F max cosine of theta, is equal to mass times the acceleration, max. Now, I'm going to rearrange this, all right? So I get that A max is equal to the F max cosine theta divided by my mass. The next thing that I'm going to do here is I really don't care for F max, all right, because that was not one of my constants or my algebraic terms that I can solve for. Therefore, I need to find some way to get rid of F max. The best way for me to do that is to solve for it in the y world, because in the y world, there's still going to be a component of F max. So in the y world, I'll change colors here. In the y world, I still have a acceleration of 0 in the y world. Therefore, my net force is equal to 0. So when I sum together these forces, I have F max sine of theta minus mg is equal to 0. Notice that there's no normal force here because we said my normal force is 0 at this moment. And notice that there was no frictional force in my x world equation because the normal force is 0. So that's an important thing to recognize here. So I want to get an expression for F max. So what I end up getting is that F max is equal to mg divided by the sine of theta. Now what I'm going to do is I'm going to take this expression and I'm going to sub it in for F max. So I get that A max is equal to mg over the sine of theta times the cosine of theta divided by m. Those m's are going to disappear, and what I get is that my maximum acceleration is equal to g times cosine of theta over sine theta. That would be a fine place to stop, or you could say that your maximum acceleration is g times cotangent of theta. All right. So let's look at where the points are coming from here. You get 1 point for right off the bat, recognizing that at this moment, the normal force should be 0. All right. You get another point for simply indicating here that your frictional force is 0. So notice, you get 2 points here just for recognizing those things. All right. Indicating them somehow. If you don't write that down, you're not going to get the points. So make sure you indicate it. Tell them that you know what you're doing. Then you get 1 point over here for getting the answer correct. So notice all of this work in here, not worth a ton if you don't write down what you're doing and why you're doing it. So if we add all this up, 4 points at the beginning, then we've got 4 points from parts B and C, so we're at a total of 8 points. Then you had 3 points here, we're at 11. Then you had 3 points on the back here for a total of 14. I feel like I might be missing one, but I'm not going to worry about it right now. So that's how you go through problem number 1. Hopefully that helps. As always, let me know if you guys have any questions.